And we're back. And at the moment, my kids are not here, but I cannot promise that'll last. So I just calculated the p-value. Again, if I'm using my z-score value, I need to make sure that I'm using 0 and 1. I screwed that up at first. What this is saying that, again, we're still assuming the null hypothesis is true because you assume it until proven otherwise. So assuming that's true, and the player makes 80% of his free throws in the long run, it is really unlikely that we would get the p-hat value that we got, or something even smaller. If it's just chance alone, it could happen, but we're finding how unlikely it is. That's the point of the p-value, to find how unlikely that possible value could be. Excuse me. So the small probability confirms our earlier decision to reject the null hypothesis. We have convincing evidence that that player is just exaggerating when he says that he's an 80% free throw shooter. So another example of this. We were looking earlier at this high school administrator who is testing for the true proportion of all students who have a part-time job. So, yeah, we already have all the data. He already confirmed that the conditions were met. So part A is explain why the sample result gives convincing evidence for the alternative hypothesis. So again, they're suspecting that it's less than 25%. So a sample was taken and they actually found what they got in the sample. So if 39 of the 200 students have a part-time job, that means we have a sample proportion of 39 out of 200. And again, I already filled out some of this because you don't need to sit there and watch me type forever. So the sample proportion of students at this school with a part-time job is p-hat 39 over 200 equals 0.195. Now 0.195 is in fact less than the national proportion. So there's some evidence. We're getting something less than 0.25, which is what was suggested in the null hypothesis. So there's some evidence to say that the proportion is less than 25%. But we need to see if it's convincing evidence. If this is really unlikely, it's so low that the null probably isn't true. So when we do this, we are going to go through those same steps again, where we're going to standardize our statistic. So that means I'm going to find my z-score. I'm going to take the statistic, which I just calculated, minus p0, the parameter in our null hypothesis, and we're going to divide by the standard error of our statistic, the standard deviation of the sampling distribution of sample proportions, which was p0, because we're assuming it's true for now, the complement of that number, divided by the sample size that we selected. And when I put that in a calculator, I get negative 1.80. So I already drew my standard normal curve. So this is our standard normal. It's also clear that it's the standard normal because I put the center at 0 and the standard deviation of 1, but either way it's nice to label it. I just found a z-score value that is below the mean. So we're going to find how likely it is that it's even lower or equal to what we just got. So that's what I'm going to do next. I'm going to find our p-value. You can use the table in the back of the book. I will expect most of you probably would rather use normal CDF. So I'm going to just say the lower value again because this happened to be another left-tailed test. Really, really, really small number. The upper is the z-score value we just found. It's the standard normal curve, so our mean is 0. The standard deviation is 1. When I put that in my calculator, I'm seeing that p is 0.0395. 59, not 95. Which honestly, I wasn't expecting it to be quite that small. I forgot how this one turns out. So what conclusion can you make? You always compare your p-value, where is it, to the level of significance that you're testing at, which should be decided in advance. So because the p-value I just found of 0.0359 is less than our level of significance. So we set this threshold for how unlikely is acceptable. And if it was less than 5%, could still happen by chance, but we're going to say not common enough that we should think that the null is still true. So I don't think the null is still true. I'm throwing it out. So if you throw out the null hypothesis, you're saying, hey, we have evidence that that alternative was the true statement here. So I'm going to say that we have convincing evidence. Before we had some evidence, now we have convincing evidence. And the thing that we're having evidence is always about the population parameter. So for these problems, we're talking about the true proportion of all students at this large high school who have a part-time job. We have convincing evidence for the alternative hypothesis, which, as a reminder, was that it's actually less than 0.25, because we found how unlikely it is that I should be getting a number like this by chance. So we have evidence that it's less than 0.25. So we don't just suspect it, we've got some evidence. However, you might have just made an error. Every time you do a hypothesis test, you run the risk of an error because you don't actually know what P is. If the decision you have made is to reject the null, the only type of error you could make is a type 1 error. A type 1 error occurs. Oh, oops, that's not what I need to actually read what I wrote. By rejecting the null hypothesis. That's the reason it's a type 1 error. We may have made a type 1 error. Now, again, we rejected the null hypothesis. I now think it's less than 25%, but I'm saying that this could be the wrong choice. It's wrong if the thing I just canceled out was actually the true thing. So if the p-value is actually equal to 0.25, we made the wrong choice. But I don't know p, so I don't know if I made the wrong choice or not. Just like when we do confidence intervals, there is a 4-step process that we kind of just did, but we're going to be very clear what those 4 steps are. You start by stating what you're doing. In this case, stating the hypotheses that you want to test, stating the significance level at which you'll be testing it, define any parameters you're going to be using. Then we always plan. When we plan, you need to state what type of test that you are doing. What we're going through today is the one sample Z test for a population proportion. Then you got to check those 3 conditions. So the do step is when I didn't list out my conditions, did I? Sorry, either way, we have them listed earlier. Do make sure you check all 3 conditions. For the do step, there are still 3 things that you're going to be doing. You're always going to state what your sample statistic is that you're using. No, not give the state. Give the sample statistic. So this is just being very clear. They took a sample. Here's what they got in this case for p hat. Then use that value to standardize it. So calculate the standardized test statistic. This is that z-score we found earlier. And then use that to find the p-value. Once you have your p-value, you're ready to conclude. You're ready to make a decision about whether or not you can reject the null hypothesis, what type of contextual summary you can make. Now, this is slightly different depending on what type of tailed test that you have. So suppose your conditions are met. To perform a hypothesis test where your null hypothesis is just, oh yeah, p is equal to some number. That's what p sub 0 is, some number. Again, we said calculate your standardized test statistic. It's a tongue twister. I don't know why I'm writing this out again, but it's not bad for me, so let's go. Not a lot of space for it, my apologies. But your p-value really, really matters about the direction of your hypotheses. So we're going to find the p-value by calculating the probability of getting a z statistic as extreme or more extreme, but it's definitely in the direction specified by your alternative hypothesis, which means if your hypothesis says that you're suspecting that the p population proportion is greater than some number, then you're going to have over here your standardized value. Your p-value will be the area to the right of it because it's greater than. The 2 that we've already looked at is they thought it was less than some number, so we'd find that space. And if it's a 2-tailed test, meaning the alternative hypothesis just says, hey, it's not P naught. It's not this number. Then we need to consider, I'm just going to put the absolute value because sometimes your test statistic will be negative, sometimes it'll be positive. But essentially, it's a symmetric curve. You're going to find the area to the right of the positive version of that test statistic and the area to the left of the negative version of the absolute value of that test statistic. So what side you're on matters for when you do these calculations. Pay careful attention to your alternative hypothesis. So example 4, I'm trying to remember what I'm doing. So another example of just putting all this crap together. We already talked about a potato chip producer. I think this was in the other video. Their supplier says they have to have certain quality standards. If more than 8% of the potatoes have blemishes, the truck is sent away. Otherwise, they're going to make chips out of it. The potato chip producer just received a truckload of potatoes from the supplier. They selected a random sample of 500. 47 of those potatoes had blemishes. We're going to use a 10% significance level to see if more than 8% of the potatoes in the shipment have blemishes. This is key here. So if it is 8%, we're fine. But if it's more than, that's whenever it gets sent away. So we want to test the assumption that this population proportion of blemished potatoes is 8% of the potatoes. Because we have some evidence, but we're looking for convincing evidence that it's actually more than that amount. And the the variable P that I'm using here is the true proportion of potatoes in the shipment with blemishes. And I need to state that I'm using a 10% significance level. So when I plan, I'm going to state how I'm going to do this test. The name of this test is a 1-sample z-test for the population proportion. Next video I'll be making is for a 2-sample z-test for a population proportion. The 3 conditions, random, 10%, and large counts. I'm not going to scroll back up and look at it, but surprise, surprise, this problem wasn't made up by me, so they remembered to put that it was actually random. There was a random sample of 500 potatoes from the shipment that were selected for examination. The 10% condition, we don't know how many potatoes are in the shipment, but it's not unreasonable to think that 500 is less than 10% of them. I don't know a whole lot about potato producing and selling, but I think this is reasonable for this problem. I hear one of my kids thudding down the stairs. I apologize in advance. Hey, buddy.
I want to play on your chair.
I don't want you to play on my chair.
Please, Mom.
I like the way you said please, but you don't need to play in here.
Because I want to play on the chair. Mom, I want to chalk. Chalk.
I'm just gonna keep going.
Hey, Mom.
What, buddy?
I never got that.
Do you want to take them upstairs and use them?
No. I can't give a funny chair.
Yeah, I've asked you not to spin in that chair. I've asked you not to be in here at all, actually. Buddy.